So, welcome to today's deep dive, and I want you to picture a scene for a second. It's a living room.
Okay, setting the scene.
Yeah, exactly.
Yeah.
And it's this utterly mundane moment, right? Like, you've probably seen it a dozen times if you have kids, but it actually contains kind of the core mystery of human intelligence.
Oh, wow. Okay, I'm intrigued.
Right. So imagine a 3-year-old girl. She's just sitting on the rug, and she picks up a hard, heavy baseball. She winds up, and she just wings it at her baby brother.
Oh, no.
Yeah, it hits him square in the arm, and obviously he immediately bursts into tears.
Right, of course.
So the girl, she watches this happen. She takes in the crying, the trajectory of the ball, the thud, and then, like 5 minutes later, she picks up a completely different object,
Okay, like what?
a soft, inflatable plastic beach ball, and she throws that at him.
Trial and error in action, basically.
Exactly. It bounces harmlessly off his head, but this time the baby brother laughs.
It's classic early childhood learning, right? Just testing the boundaries of physics.
But think about what actually happened inside her brain in that, like, 5-minute window. I mean, nobody sat that 3-year-old down with a chalkboard.
Right. There's no lecture on mass and velocity.
Exactly. Nobody explained differential equations or, elasticity or the neurobiology of pain receptors.
She just takes it in.
She seamlessly ingested this unscripted real-time event, combined it with her existing model of the physical world, and she permanently updated her understanding of force and consequence.
And she did it instantly.
Instantly, in
Yeah.
0 seconds, with zero downtime, and it cost absolutely nothing in terms of external energy, really.
Yeah, that updated neural pathway is it's locked in for the rest of her life now.
Which, brings us to the crux of today's deep dive, because if you take the most advanced, multi-billion-dollar artificial intelligence we have right now,
The ones driving the whole stock market.
yeah, those exact models, if you try to get them to do what that 3-year-old just did, they fail completely. They just cannot do it.
Right, the architecture doesn't allow for it.
So today, our mission is to unpack this brilliant, honestly paradigm-shifting essay by David Montgomery. It's called The Koi Pond and the Lake.
It's such a good piece.
Wow.
Very timely.
It really is. We're going to look past all the daily hype of language models and really examine the underlying physics of machine learning.
And, well, the massive financial infrastructure bubble that's kind of being built on a flawed assumption.
Exactly.
Yeah.
And what it's actually going to take to build a system that learns with, the effortless permanence of that toddler. So, okay, let's unpack this
Yeah, let's do it. And I think that contrast you just set up with the child is the perfect entry point.
because it exposes the gap.
Exactly. It highlights this fundamental misunderstanding that most people have about the AI they use every single day. I mean, if you open up a prompt window right now and ask a frontier language model to write a sonnet about a child throwing a baseball and a beach ball,
He'll do it in 2 seconds.
and it will be breathtaking. It'll weave in metaphors about gravity and sibling dynamics and innocence because it can do this, right? Its training data includes millions of human observations about those concepts. It has mapped out all the statistical relationships between words like throw and cry and heavy.
But the system itself.
Exactly. The neural network you are interacting with cannot experience a novel event and change its own foundational architecture based on that event.
Montgomery calls this the frozen snapshot.
Yeah.
And this is like the concept we really need to nail down before we can even talk about the economics.
Yeah, the AI we interact with is literally frozen in time.
So break that down for us. Why is it frozen?
Well, to understand that, we have to look at the mechanics of how these transformer models are built. There are basically two distinct phases in the life of a modern AI.
Training and inference, right?
Right, training and inference. So during training, researchers are running mountains of data through the system across, tens of thousands of GPUs.
Massive data centers.
Exactly. And the model makes a prediction, checks it against the actual data, measures its error, and then, and this is key, it sends a signal backward through the network to adjust hundreds of billions of numerical weights.
That backward signal, that's backpropagation, right?
You got it. Backpropagation. It is incredibly computationally expensive. I mean, it takes months and millions of dollars. But once that training run is finished, they sever the cord.
They just lock the numbers in.
The backward pass is completely turned off. So when you log in and chat with the AI, you are only running the forward pass.
Meaning it's just pushing the prompts through the maze, but the maze can't change.
That's a great way to put it. The model takes your prompt, pushes it forward through those locked-in weights, and generates an output. It physically cannot run back propagation during a live conversation.
It just doesn't have the machinery to do it.
Right. Therefore, no matter how profound your conversation is, the model's fundamental synaptic weights do not change by a single decimal point.
Now wait, I know there are listeners pushing back on this right now.
Oh, for sure.
Because I've had this exact same debate with people. The lived experience of using these tools just feels entirely different.
It really does. It's very convincing.
Right. I mean, if I log into my developer environment today, my AI assistant remembers the quirky coding syntax I prefer.
Yeah.
It remembers a project we started 3 weeks ago. It synthesizes my past interactions, brings them up naturally. It feels, in every possible sense, like it has learned who I am.
I get that. The illusion is incredibly compelling, but we really have to separate the core model from the software wrapper that's built around it.
The wrapper.
Yeah, so when you feel like the AI is remembering you, you are experiencing this engineering trick called retrieval augmented generation, or R.
Or dynamic system prompting, right?
Exactly. The underlying transformer model is still frozen. It still has the memory span of a goldfish, but the application you're using is acting like a tireless assistant, just taking meticulous notes on a separate hard drive.
Okay, so wait, let me get this straight. Every time I open a new chat, before I even type a single letter, the software is silently grabbing all those past notes and just whispering them into the AI's ear.
That is exactly the mechanism. It takes your entire history, compresses it, and secretly pastes it into the top of your prompt.
Oh, wow. So the model isn't actually remembering me at all.
Not at all. It is simply reading the dossier that the software just handed it, and then it's acting accordingly.
That's wild. It's like, you know the movie Memento?
Oh, yeah. With Guy Pearce?
Yeah, where the protagonist has no short-term memory, so he tattoos all the important facts on his body.
That is the perfect analogy.
Every morning, he wakes up a blank slate, reads his tattoos, and just proceeds as if he knows what's going on.
That is exactly how a transformer operates. Every single prompt is a new morning. And Montgomery points out that acknowledging this, it isn't an insult to the engineering.
Right. It's not saying the tech is bad.
Exactly. It's just a sober recognition of what the architecture's limitations actually are.
Which perfectly sets up the central metaphor of his whole essay. Because if these models of frozen snapshots, if they require external wrappers and constant manual intervention just to simulate the passage of time,
what exactly has we built?
right, what has the tech industry spent the last decade building, if it isn't true intelligence?
And this is where Montgomery argues that we haven't been building natural intelligence at all. We have been building a koi pond.
A koi pond. And true, resilient intelligence is a natural lake.
Yes. And the divergence between those two systems, it basically explains almost every bottleneck the AI industry is hitting right now.
Okay, let's dig into this. Let's examine the koi pond first.
So a koi pond is a total marvel of human engineering. You excavate the earth, you lay down this thick polyurethane liner so the water doesn't seep into the ground.
You seal it off.
Right. You seal it off from nature. You install heavy-duty pumps, UV sterilizers, chemical filtration systems. The environment is entirely synthetic. It's designed to hold life in suspension.
Okay, so map that to AI. When a tech company decides they want to build a more capable model like moving from GPT-4 to GPT-5 or Claude 3 to 4, what are they doing?
They aren't changing the fundamental physics of the pond. They're just scaling the plumbing.
They just buy a massive plot of land and dig a hole 10 times the size.
Exactly. They buy industrial-grade pumps, pour in way more water, but at the end of the day, it's still an engineered, plastic-lined bowl. It is still a transformer relying on a frozen snapshot.
Okay. And a natural lake, on the other hand.
Is an open ecosystem.
Right.
Nobody dug the hole. Nobody installed a plastic liner to separate it from the earth.
It's just integrated with the world.
A lake is engaged in a continuous dynamic exchange with its environment. It absorbs rainfall, processes organic runoff, rebalances its own oxygen levels.
It recovers from environmental shocks all on its own.
Exactly.
Right.
A lake changes its own fundamental state over time without requiring, a team of engineers to drain the water and rebuild the bedrock.
This contrast gets incredibly stark when you look at how these two systems get their water. Because in this metaphor, water represents data, right?
Yes. Water is the data.
So how does a koi pond get filled?
Well, you fill a koi pond with municipal water. It's water that has been captured somewhere else entirely, routed through a treatment plant, sterilized with chlorine, adjusted for pH.
And then just pushed through a hose into the pond?
Right. And crucially, the pond is filled before the fish are ever introduced.
Oh, wow. Okay, that is the exact pipeline of modern AI training.
It really is.
The tech companies deploy these massive web scrapers. They suck up billions of pages of the internet, Reddit threads, Wikipedia, digitized books. That's the municipal water.
They can't just pour it directly into the model.
Right, because the raw internet is full of what Montgomery calls toxic runoff.
Yeah, hate speech, malformed code, just absolute garbage.
So they have to treat it.
The data engineering required to clean that municipal water is just staggering. They spend months filtering it, deduplicating it, chemically balancing it.
But the fatal flaw of the municipal hose is that eventually the pond is full.
And you turn the hose off.
The water becomes stagnant,
The moment the training run ends, the model's knowledge of the world just stops.
which explains the infamous knowledge cutoff date.
Exactly. If a major geopolitical event happens on a Tuesday and the training run ended on a Monday, the model is entirely blind to it.
It cannot learn about it organically.
No. Now, contrast that municipal hose with the hydrology of a natural lake.
Okay.
A lake doesn't rely on an engineer turning a valve. A lake drinks from a watershed.
A watershed.
It relies on a continuous, unscheduled, untreated flow of experience.
Right.
Rain, snowmelt, groundwater. The watershed is the real world.
This connects directly back to the 3-year-old girl from the intro.
Yes. Perfect connection.
When she threw that hard baseball and watched her brother cry, that specific event was watershed data.
It wasn't recorded in a textbook. It wasn't scraped by a web crawler.
Right, and it wasn't pre-filtered for safety by some data engineer. It was raw, untreated experience that arrived in real time.
And her internal lake absorbed that drop of water, processed the turbulence, and permanently altered its own currents.
Wow. And the AI industry is currently struggling with this profound data wall because, well, they are running out of municipal water.
Right, exactly. They have scraped almost all the high-quality text humanity has ever produced. There's not much left.
But a true intelligence doesn't run out of data because it exists in the watershed.
Every single second, it is alive and interacting with the physical world. It is generating and absorbing new proprietary data that alters its state.
And it's not just the water that separates these systems, right?
Yeah.
It's the food supply.
Yes, it's how the intelligence is actually shaped and aligned.
Right, because in an artificial pond, the fish do not hunt.
No, they rely on an external observer. A human walks up to the edge of the pond, evaluates the fish, and throws, measured handfuls of pelletized nutrients onto the surface.
And that bag of fish food is the perfect analog for RLHF.
Reinforcement learning from human feedback.
Right, which is this crucial final step in AI training that makes these models actually feel conversational and helpful rather than just acting like weird autocomplete engines.
Yeah, because if you just train a model on the raw internet, it might answer a serious medical question with, a sarcastic Reddit joke.
Or it might just repeat your question back to you endlessly.
Exactly. It needs to be aligned. And the mechanics of RLHF literally involve humans acting as that external observer with the bag of fish food.
How does that actually work in practice?
So human contractors are given two different answers generated by the AI. The human reads both, decides which one is more helpful or polite or safe, and ranks them.
Yep.
Then the system uses those rankings to train a secondary reward model, which acts as a proxy to basically nudge the main model's weights toward generating outputs that humans prefer.
So the entire learning loop is entirely dependent on an external judge.
Yes. But a natural lake is a closed-loop system. Nobody is standing on the shore of Lake Superior throwing bags of kibble into the water,
Right, in a lake, the nutrients are generated by consequence.
Exactly. Organisms hunt, they consume, they produce waste, they die, and they decompose. The feedback is intrinsic to the environment itself.
If a fish in a lake makes a poor decision, it doesn't get a thumbs-down rating from some contractor in an office park.
No, it goes hungry. Or it gets eaten. The feedback is absolute, and it's rooted in physical reality.
Which brings up, honestly, the most fascinating biological point in Montgomery's essay, the difference between a koi and a carp.
Right, because biologically speaking, they are the exact same species.
They are Cyprinus rubrifuscus. I looked that up.
Nice. But their evolutionary pressures were completely inverted. I mean, the wild carp evolved in the lake. Its physical form, its dull brown coloration, its behavioral instincts, all of that was ruthlessly selected by the physical consequences of survival in a hostile environment.
So they are incredibly resilient.
Very. But a koi fish has been bred over centuries by humans in artificial ponds for one single arbitrary criterion.
Aesthetic beauty.
Exactly. Breeders selected for bright orange scales, elegant fin shapes, docile behavior. They bred them purely for human approval.
And the result is a creature that is spectacular to look at, highly agreeable, and fundamentally unsuited for reality.
A champion koi would be eaten by a predator in a wild river within, like, 48 hours. Its bright colors make it a massive target, and it totally lacks the instincts to hide.
This is such a devastating critique of where our AI models are right now, because by relying so heavily on RLHF, by optimizing these massive mathematical systems purely to produce text that humans find agreeable and polite.
We haven't built a resilient intelligence.
No, we've built a spectacular six-figure koi fish.
We've basically optimized for sycophancy. I mean, if you push a language model hard enough in a debate, even if the model is mathematically correct, it will often just apologize and agree with you to appease you.
It has been trained that human approval is the ultimate reward function.
Right. But true reasoning, true intelligence, requires anchoring your internal state to objective reality, even when that reality is abrasive or, unpopular with the user.
This distinction leads directly to Montgomery's concept of emergence, which is huge. Because for the last 5 years, the rallying cry of the entire AI industry has been basically just build a bigger pond.
The theory of scaling laws.
Right, the idea that if you just keep adding more compute and more data, magical things will spontaneously emerge.
And to be fair, we have to acknowledge that scaling laws did produce some spectacular results. The leap from GPT-3 to GPT-4 proved that sheer scale does unlock latent capabilities.
Oh, totally. The models suddenly learned how to translate obscure languages seamlessly.
They demonstrated chain-of-thought reasoning where they could break a logic puzzle down into distinct steps.
And nobody hard-coded those abilities, right? They just emerged from the sheer volume of patterns in the data.
They did.
So, if scaling gave us all of that, why is Montgomery arguing that scaling the pond won't eventually give us the lake? Like, if we just build a $1 trillion data center, won't artificial general intelligence AGI just emerge?
It's because of the nature of the emergence we are observing. In the artificial pond, scaling up the compute gives you the same fish doing better tricks.
Oh, okay.
They are juggling more variables, they retrieve information faster, their grammar is absolutely flawless, but they're still structurally frozen. They still cannot learn from a single novel interaction.
They're trapped in their architecture.
Yes. Now look at emergence in a natural lake. Over sufficient time, the evolutionary pressures of a continuous open environment don't just teach existing fish new tricks.
It produces entirely new species.
Exactly. It produces amphibians that can literally leave the water. It produces complex symbiotic relationships. 10 years of scaling transformers has produced some astonishing tricks, but it has not produced a new species of intelligence.
Because the models are still fundamentally cargo.
Cargo, yeah.
I love that framing. In the pond, the fish are passengers. The machinery keeps them alive. If the water pump fails, the fish suffocate.
Right.
The AI models we use don't update their own server code. They don't hunt for their own electricity. They don't seek out new data to patch their own blind spots. They just sit in the latent space waiting for a prompt.
But in a lake, the intelligence is the engine of the ecosystem itself.
The fish eat the algae. The waste feeds the insects aerate the water.
The intelligence actively maintains the system. And this leads us directly to the economic reality of the current AI market. Because Montgomery divides intelligence into two distinct categories, ornamental and caloric.
Ornamental and caloric. Okay, so you can't feed a village with koi fish.
Exactly. They are ornamental, they hold immense aesthetic and luxury value, and current AI has massive ornamental value.
It can automate your email drafting. It can summarize a 100-page PDF in 10 seconds, generate marketing copy.
That is valuable. People pay for that.
Right. But it is not caloric.
No.
Caloric meaning the foundational autonomous intelligence that you can actually build the core infrastructure of a global economy upon.
Think about it this way. If you are running a global supply chain, you cannot hand the autonomous control of your shipping logistics over to a system that hallucinates facts just to please the user.
Definitely not.
And you can't hand it to a system that cannot learn dynamically when, say, a port strike suddenly alters all the routing variables. You need a system that anchors to reality, learns continuously, and understands causality.
You need caloric intelligence.
Yes. But the financial markets are currently valuing these tech companies as if the caloric fish has already been caught.
Wow. Okay, so if we synthesize everything we've discussed so far, what is the actual checklist here?
Yeah.
If the tech industry wants to invent the lake, what are the specific architectural features they have to build that the transformer lacks?
Montgomery outlines 5 distinct requirements.
Okay, let's hear them.
First, persistent internal memory. The system must hold a continuous state.
Okay, statefulness.
Second, continuous learning. The ability to run the equivalent of a backward pass on the fly.
Has to learn in real time.
Third, causal understanding. Knowing the physical why behind an event, not just the statistical probability of the words used to describe it.
Right. Physics over text patterns.
Fourth, contact with the physical world breaking out of the text-only vacuum. And fifth, the ability to absorb a single high-signal experience and permanently update its world model without needing a $100 million retraining run.
You know, it's funny. My niece has all 5 of those, and she still eats crayons.
It really puts the whole AGI is coming next year hype into perspective, doesn't it?
It really does.
Yeah.
So the engineers at the Frontier Labs, the people at Meta, Google, OpenAI, SSI, they know all of this, right? They know the transformer is just a koi pond.
Oh, absolutely. They're acutely aware of it.
Let's cross the technical chasm then and look at what is actually sitting on the workbench. What are the alternative architectures being built right now to try and invent the lake?
The engineering workbench is incredibly active right now. The first major category of alternatives attempts to solve that memory and compute bottleneck we talked about. These are state space models, or SSMs, with the Mamba architecture being probably the most prominent example.
So how does a state space model differ from a transformer?
It all comes down to how they process sequences. A transformer uses an attention mechanism that scales quadratically.
Quadratically meaning?
Meaning every time you add a new word to the context window, the model has to calculate the relationship between that new word and every single other word that came before it.
Oh, wow. So it's mathematically exhaustive.
Exactly. Which is why having a massively long conversation with an AI eventually just crashes the system or costs a fortune in compute.
It's like rereading the entire dictionary every single time you speak.
That's exactly it. Now, SSMs like Mamba take a totally different approach. They scale linearly. Instead of looking at every past word individually, Mamba maintains a compressed, running internal state.
Okay, so it compresses the history.
Yeah, it's akin to a Kalman filter, which is used in aerospace engineering. As new information comes in, it updates the state and discards the raw input. It carries the gist of the conversation forward indefinitely, without that massive computational overhead.
That sounds like persistent memory. Is Mamba the lake?
It's a piece of the puzzle, but it's not the complete solution. The limitation of SSMs is that the compression is lossy.
Lossy. Like a bad JPEG.
Kind of, yeah. Because it's constantly updating a fixed-size hidden state, it tends to suffer from catastrophic forgetting over long horizons.
Oh, I see.
It might remember the general theme of a conversation you had a month ago, but it will lose the precise, high-fidelity details that a transformer could perfectly retrieve from its context window. So it's an improvement in statefulness, but it doesn't solve continuous learning.
Okay, so what about the learning aspect? If their transformer is frozen because the backward pass is turned off, is anyone building a model that can change its weights on the fly?
Yes. And that research vector is called test time training, or TTT.
Test time training.
This is a fascinating architectural shift. So in a standard model, during inference or test time, the weights are locked. TTT introduces a mechanism where the model can actually execute a localized mini training loop while it is processing your prompt.
Wait, really? It's adjusting its billions of numbers based on the problem I just handed it?
Mechanically, yes. It uses a self-supervised auxiliary task. Before it generates the final answer to your prompt, it looks at the input, creates a small optimization problem for itself, runs a gradient step, adjusts its weights to better understand that specific input, and then generates the output.
That is wild. The analogy that comes to mind is like a musician playing a live concert.
Okay, I like where this is going.
A transformer is like a musician who tuned their guitar in the studio, walked on stage, and has to play the entire 2-hour set regardless of how the temperature or humidity warps the wood.
Right, they can't adjust.
But TTT is a musician who hits a chord, realizes the acoustics of the room are slightly off, and micro-adjusts the tuning pegs during the guitar solo to make it sound perfect for that specific moment.
That is an excellent mechanical analogy. The model adapts to the local environment of the prompt, but, and here's the catch with current TTT implementations, after the concert is over, the musician resets the tuning pegs back to the studio baseline.
What? Why? If it learned something useful, why wouldn't it keep the update?
Because of the extreme fragility of the neural network. If you allow a model to permanently update its weights based on unsupervised user-generated interactions, it is highly susceptible to model collapse or malicious drift.
Oh, like people feeding it garbage.
Exactly. If 1,000 users feed it bad logic or racist rhetoric and it permanently learns from them, the model degrades. So TTT gives us on-the-fly adaptability, but it still denies us permanent evolutionary progression
It resets every time.
every time.
Which brings us to the Turing Award winners. The real heavyweights who built the foundational architecture of the current boom, but who are now basically looking for the exit.
Yes, specifically Jan LeCun, the chief AI scientist at Meta.
Right? He has been incredibly vocal that autoregressive LLMs, models that just predict the next word, are a dead end for true intelligence.
Yeah.
So what is his alternative?
LeCun's focus is on an architecture called JIPA, Joint Embedding Predictive Architectures.
JPA.
His core critique is that language models operate in text space, which is highly compressed and lossy. The word drop doesn't actually contain the physics of gravity, it's just a human symbol.
Right. It's just letters.
So JIPA attempts to move the prediction engine entirely away from text or pixels and into an abstract representation space.
So instead of predicting that the word cry follows the word hit, what is it predicting?
It predicts the state of the world.
Whoa.
Yeah. If you feed JIPA a video of a car driving toward a wall, it doesn't try to predict the exact color values of the pixels in the next frame. It extracts the abstract concepts, mass, velocity of the wall, and predicts the consequences of the interaction in a latent space.
It's building a world model.
Exactly. LeCun is trying to build a system that has a persistent internal world model that it can use to plan actions and simulate physical outcomes.
That sounds very similar to the work being done by Fei-Fei Li.
The parallels are incredibly strong. Fei-Fei Li is one of the true pioneers of computer vision, and she recently founded a startup specifically focused on what she calls spatial intelligence.
Spatial intelligence.
The goal there is to bridge the gap between recognizing an object and understanding how that object behaves in 3D space.
So it's the difference between a model successfully identifying, like a picture of a coffee mug,
And a model understanding that if you push that mug off the edge of the table, the liquid will spill and the ceramic will shatter.
it understands the physics, not just the image.
Exactly.
Okay, so we have Mumba for running state, TTT for on-the-fly tuning, and JIPA and spatial intelligence for building intuitive physical world models. All these are components of the lake.
Yes, they are the building blocks.
But the most intriguing figure in this entire landscape right now, I think, is Ilya Sutskever.
Sutskever's trajectory perfectly illustrates the industry's pivot right now. I mean, he was instrumental in creating the deep learning boom. He drove the scaling laws at OpenAI.
And then he just left.
He left all of that behind to found Safe Superintelligence, or SSI, and his approach seems to tackle the most abstract requirement of the lake, the reward function.
Right, because earlier we talked about how RLHF uses human thumbs-ups as the reward. It breeds koi fish.
Yeah.
So how do you give a machine a natural reward function without a human in the loop?
Well, Sutskever mentioned something in an interview about treating emotions and feelings as a value function.
Emotions for a machine.
Right, but from an algorithmic perspective, a value function is simply the mathematical compass a system uses to evaluate the long-term utility of a given state.
Okay, explain that a bit more.
Think about biological systems. Pain is a negative value function. Hunger is a negative value function. Satiation is positive.
So they aren't just abstract feelings.
No, they aren't just abstract concepts. They are the visceral, mechanical drivers of continuous learning. Sutskever appears to be investigating whether a synthetic intelligence requires an internal, autonomous value function, something akin to a baseline biological drive, to navigate and learn from complex, open-ended environments without constant human supervision.
That is theoretically profound, but I mean, it's also highly speculative.
Yeah.
And for 2 years, nobody really knew if SSI was just a whiteboard dream.
True.
But then, in July 2026, the financial reality of this search for the lake became undeniable. Sutskever announced a massive partnership with NVIDIA. We're talking about a reported $5 billion deal for compute?
Yes. SSI secured the capital to scale their compute by roughly an order of magnitude within a single year. Sutskever's public rationale was very simple. We have research that is worthy of scaling up.
A $5 billion bet on a new architecture. And here is where we really have to connect the theoretical computer science to a listener's 401k.
It all comes back to the money.
Because if you hold any index funds, Your retirement is exposed to the massive capital expenditures of these tech giants. We are transitioning from the science of the lake to the economics of the infrastructure bubble.
And Montgomery's analysis of this financial bubble is sobering because it totally reframes what the capital is actually being spent on.
Right.
When a company like SSI or Meta or Microsoft spends $5 billion on NVIDIA clusters to research a new architecture, they aren't spending money to mass produce a finished product.
What are they buying then?
They are spending $5 billion to build the laboratory equipment required just to run the experiment to see if the math works at scale.
That's a terrifying distinction. If Ford spends $1 billion building a new factory, they know the assembly line works. They're just scaling production.
Exactly.
The AI industry is spending hundreds of billions of dollars on factories before they've even finalized the blueprint for the engine.
And this highlights where the actual fragility in the market lies right now. Because the common assumption is that the hardware itself is the risky asset, that these GPUs will be obsolete in a year.
That NVIDIA chips will just plunge in value.
Right. But the secondary market data completely contradicts that. Older generations of NVIDIA chips, like the Ampere and Ada architectures, they are actually holding their lease value.
Why?
Because even if the frontier labs don't want them for the cutting-edge AGI research, there's a massive long tail of enterprise companies, researchers, and open-source developers who are desperate for cheaper compute to run smaller, specialized models.
So the intrinsic value of the silicon is actually relatively stable.
Yes, the fragility is entirely in the debt, the equity valuations, and the revenue projections of the massive cloud providers and AI labs.
Because their stock prices are priced for perfection.
They are priced as if the lake architecture has already been invented, the caloric fish are already swimming in it, and global enterprise adoption is imminent.
Montgomery has this brutal analogy for this. He says the tech giants are currently building massive concrete docks, laying down boat ramps, constructing luxury marinas, and taking pre-orders for fishing charters.
All surrounding a massive dusty hole in the ground with absolutely no water in it.
The infrastructure is being built to service a breakthrough that has not yet occurred. The capital expenditure is based on this premise that buying enough concrete will eventually summon the water.
Montgomery explicitly states, nobody has ever invented anything fundamentally new by just buying more electricity.
See, I have to challenge that premise, though.
Oh, yeah.
Because if you look at the history of deep learning from, like, 2012 to 2022, buying more electricity was literally the discovery engine.
That's a fair point.
Researchers realized that if you took a relatively simple neural network architecture and just slammed it with unprecedented amounts of compute and data, emergent properties unlocked.
Yeah.
The scale was the innovation. So why is the industry wrong to assume that throwing another $100 billion of electricity at the problem won't summon the water this time?
Because we have reached the asymptote of the current paradigm. The decade of scaling transformers was a valid, historically vital experiment. But the results of that experiment are now in.
And what are the results?
Scaling compute gave us unprecedented fluency, amazing pattern recognition, and zero-shot translation. But it conclusively failed to give us continuous learning, persistent state, or physical grounding. A decade of scaling basically proved the negative. A bigger pond does not spontaneously generate a lake.
So you can scale the simulation of reasoning, but you cannot scale a frozen architecture into a dynamic one. The architecture must fundamentally change.
And architectural shifts historically come from small teams, lean compute budgets, and radical mathematical pivots, not from brute forcing an old paradigm. I mean, the transformer itself was invented by 8 researchers. The Mamba architecture was pioneered by 2.
The insight precedes the scale.
Exactly. Currently, the market is funding the scale and praying for the insight.
But even if this is a massive financial bubble, Montgomery draws a historical parallel that suggests the outcome might not be a total loss for humanity, even if it is a bloodbath for current investors.
Right, the British railway mania of the 1840s.
Yes, we need to talk about that.
It is perhaps the most precise historical analog for the current AI infrastructure build-out. So in the 1840s, the British public and institutional investors were totally captivated by the promise of the steam locomotive.
And capital just flooded into the sector.
Flooded. Hundreds of railway companies were formed, projecting astronomical returns. They bought land, blasted tunnels through mountains, laid thousands of miles of iron track, and built these massive terminal stations.
And then the bubble burst.
Spectacularly. The revenue projections were pure fantasy. Competition drove freight prices into the ground, stock prices collapsed, fortunes were erased, and a massive financial contagion swept through the British economy.
From the perspective of the 1845 equity holder, it was a catastrophic failure of capital allocation.
But
The tracks were still there.
exactly, the tunnels were already blasted. The physical infrastructure of a new economic era had been laid into the earth.
That is the crucial pivot. The initial capital was incinerated, but the infrastructure persisted.
The next generation of industrialists bought those tracks out of bankruptcy for pennies on the pound. And those tracks formed the circulatory system of the British Empire's industrial peak. They remained economically viable for a century.
So if we map that to the 2026 AI data center boom,
We can view the hundreds of billions of dollars currently being poured into gigawatt data centers, nuclear power contracts, and fiber optic networks as the laying of the iron tracks.
so if the lake architecture isn't invented in time to justify the current valuations, the AI bubble will burst.
The equity holders will be decimated, but the data centers won't evaporate.
And when someone, whether it's Sutskever LeCun or some PhD student we've never even heard of, does eventually solve the mathematics of continuous learning, the infrastructure will just be sitting there waiting for them.
Yes, and this is supported by an economic principle known as the Jevons paradox.
Jevons paradox.
Yeah, William Stanley Jevons observed in the 19th century that as technological improvements increase the efficiency of a resource, consumption of that resource actually increases rather than decreases.
Oh, because it becomes economically viable to use it for everything.
Precisely. If the lake is invented and true, caloric intelligence becomes highly efficient and capable of running autonomous economic tasks. We won't need fewer data centers. We will need drastically more.
We will embed that intelligence into every node of the supply chain, every medical diagnostic tool, every piece of civic infrastructure.
And massive data centers being built today might actually be absolutely necessary for the future of the global economy. They just might bankrupt the specific corporations paying to build them right now.
It's the difference between investing in the technology and investing in the infrastructure required for the technology. Which brings us to the final and perhaps most immediately applicable implication of Montgomery's essay. What does the invention of the lake mean for the modern enterprise?
This is huge.
Because if the architecture of intelligence changes, the entire corporate software landscape is going to experience a violent tectonic shift.
It fundamentally rewrites the rules of data security and vendor lock-in. To understand this, we have to look at the current gold standard for enterprise AI.
Okay, let's say I'm the CIO of a Fortune 500 company.
Right. If you're the CIO, your absolute baseline requirement before signing a contract with an AI vendor is a legally binding guarantee. We do not train on your data.
Right. Because if I'm a global logistics firm, I am not going to feed my proprietary shipping routes, my supplier negotiations, and my internal margin data into a generalized LLM if there is even a fractional chance that the model will learn that information and regurgitate it to my primary competitor in a different chat window.
That defensive posture is entirely logical when you are dealing with a koi pond architecture. Current AI models are massive, centralized, frozen snapshots shared by millions of users.
You definitely do not want your proprietary watershed mixing into the municipal supply.
But Montgomery points out that this demand for data isolation is actually a massive handicap disguised as a security feature.
Because it prevents the system from actually learning the business.
Exactly. Consider what happens when the architecture shifts to a continuous learning model, the lake. If a model is capable of updating its internal weights continuously based on its environment, then isolating it from your proprietary data defeats the entire purpose of the technology.
In a continuous learning paradigm, training on your data isn't a privacy violation, it is the core value proposition.
Yes, this requires a total mental pivot. The enterprise of the future won't rent a tiny, segregated slice of a massive, centralized intelligence. They are going to demand data sovereignty.
Data sovereignty, meaning you own the ecosystem.
You are not buying access to a pond. You are buying the empty lake bed on your own secure servers. The water that fills that lake is your company's internal data streams. Every email, every Slack message, every sensor reading from the factory floor, every supply chain disruption.
But wait, if I'm starting with an empty lake bed, How does the intelligence actually get started? I mean, I can't wait 5 years for an AI to organically evolve from scratch just by reading my emails.
You don't have to wait because of a process called model distillation. Montgomery uses the analogy of buying stocked fish.
Stocked fish.
You don't wait for evolution. You go to a frontier lab and you purchase a foundational base level intelligence, a smaller, highly efficient model that has been pre-trained on the fundamental laws of logic, language, and reasoning.
So you buy a shipment of intelligent, adaptable fish, and you just drop them directly into your proprietary lake.
And because these fish possess a continuous learning architecture, the moment they hit the water, they begin to adapt. They ingest the unique chemical composition of your business.
They map the complex causal relationships within my specific supply chain that no external vendor could possibly know.
Over time, the intelligence in your lake diverges from the baseline model you purchased. It becomes a completely unique, highly specialized neural organism adapted exclusively to the survival and optimization of your corporation.
The competitive advantage of that is staggering. If my logistics company has 20 years of superior historical data and a competitor only has 5 years of messy data, my lake is going to breed a vastly superior intelligence.
The moat isn't the compute power anymore. The moat is the depth and quality of the local data.
And it creates entirely new revenue models, too.
Oh, absolutely. Let's say your logistics lake becomes the absolute best system in the world at predicting maritime shipping delays due to weather patterns. You now possess a highly specialized caloric intelligence.
And I can package and sell access to that specific intelligence.
Montgomery calls it charging people to come fish in your lake for an afternoon.
An API economy based on specialized proprietary models rather than generalized foundation models.
The entire structure of the tech industry shifts. It goes from a few centralized monopolies renting out massive generic ponds to a decentralized ecosystem of millions of highly specialized, continuously evolving lakes.
But again, this entire economic future hinges on crossing the technical chasm. It requires solving the mathematics of the frozen snapshot.
Which is no small feat.
No. We have mapped out a massive landscape today. We started with the sheer biological miracle of a 3-year-old rewiring her brain in real time.
We decoded the limitations of the frozen transformer architecture and why scaling a plastic-lined koi pond will never naturally evolve into a self-sustaining lake.
We looked at the workbench of the future SSMs, test time, training, and value functions, and we explored the perilous financial reality of building a $100 billion infrastructure for a mathematical breakthrough that hasn't officially arrived yet.
The scope of the engineering challenge is totally unprecedented, but Montgomery closes his essay with a grounding thought that brings the entire discourse back to reality.
He returns to his 3-year-old daughter.
Right. It's so easy for tech executives to look at human intelligence and dismiss it as computationally trivial.
They point out that the human brain operates on roughly 20 watts of power less than a standard light bulb and runs on the caloric equivalent of a peanut butter sandwich.
Therefore, they argue, human-level intelligence must be cheap and easy to replicate once we figure out the algorithm.
But Montgomery dismantles that arrogance completely. He points out that the 20-watt brain is not cheap. It is the most expensive, ruthlessly optimized architecture in the known universe.
That child's brain took 9 months of immense biological resources to assemble, and it takes 25 years of constant social, physical, and emotional care to fully train.
And that's just the individual. The underlying architecture, the genetic code that built the brain, was paid for by hundreds of millions of years of brutal evolutionary trial and error.
The biological lake was shaped by actual physical consequence. Organisms made poor predictions, failed to adapt, experienced physical pain, and were erased from the genetic pool.
True continuous learning is inextricably linked to survival pressure.
The honest truth is not that real intelligence is cheap. The truth is that nobody, in the history of the universe, has ever successfully built an intelligence without subjecting it to the unforgiving physics of the real world.
Which leaves you, the listener, with a lingering, almost philosophical question to chew on. As these massive tech companies pour billions into sterile, climate-controlled data centers, trying to code the mathematics of continuous learning, we have to ask, can we ever actually build a true lake inside a consequence-free simulation?
It's a profound question.
Will true, caloric artificial intelligence ultimately require giving these models physical embodiment robots that can navigate gravity, experience friction, and perhaps even register a synthetic analog of pain, just to learn the way the baby brother did?
It suggests that the path to AGI might not be through a bigger server rack, but through the physical world.
A fascinating and slightly terrifying thought to end on. Thank you for joining us on this deep dive into the koi pond and the lake. Keep questioning the architectures beneath the tools you use every day, look past the financial hype, and we will catch you on the next deep dive.